For the past 323 years, tension has been building as tectonic plates collide here in the Cascadia subduction zone. When this tension releases, an earthquake 45 times more powerful than California's most destructive earthquake in 1906 will occur. The consequences of this earthquake are unimaginable, and geophysicists predict that this earthquake has a terrifying 20 to 30% chance of occurring within the next 50 years. This earthquake will take thousands of lives and accumulate over $200 billion in damages. This video will cover how the earthquake will impact our future, why the subduction zone is so dangerous, and current research being done to understand the region and mitigate its threat. The Cascadia subduction zone lies here, in the Pacific Northwest, roughly 112 to 160 kilometers off the Pacific coastline. It extends from northern California to Vancouver Island in Canada. The region is where the Juan de Fuca, Explorer, and Gorda tectonic plates are subducting beneath the North American plate. Until recently, the Cascadia subduction zone was thought to be incapable of producing great earthquakes of magnitude 8 or 9. However, recent geophysical modeling and analysis has shown that such catastrophic events have occurred before in the region, and it's only a matter of time before they happen again. In 1986, paleogeologist Brian Atwater dug at Nia Bay, Washington, and discovered triglycan. The plant species, more commonly referred to as aerograss, is native to wet, alkaline soil, and its discovery beneath the layer of sand on Nia Bay was evidence that the ground had suddenly sunk under sea level. The event had occurred so rapidly that a layer of sand sealed the air and preserved the aerograss. The plant species was centuries old at the time of discovery, and was Atwater's first clue to something bigger happening in the Pacific Northwest. 1 year later, in 1987, Atwater and Dr. David Yamaguchi went on an expedition along the Copalis River. The pair discovered a section of land containing dead, gray stumps that were a sign of sudden inundation, which quickly killed all life there. The area became known as a ghost forest, which had occurred due to the land plummeting 2 meters because of an earthquake. Using tree ring dating, they discovered that the event occurred sometime between the winter of 1699 and 1700. Back at the aerograss site, Jody Bourgeois and a team of researchers discovered the sudden sand cover was the result of a tsunami surge. Further research by the United States Geological Service discovered that the coast from British Columbia to Oregon had fallen due to a massive earthquake. This land was quickly covered with sand due to a subsequent tsunami. In 1996, seismologist Kenji Satake supplemented research from Atwater with evidence for tsunamis across the Pacific. Japanese records showed that a 16-foot tsunami struck Honshu Island in the year 1700. Since no earthquake appeared to have produced it, the tsunami was dubbed an orphan tsunami. However, the study found that a magnitude 9 earthquake on January 26, 1700 at 9:00 p.m. in the Pacific Northwest had led to the tsunami on Honshu Island that occurred 10 hours earlier. Thus, the Cascadia subduction zone was shown to be capable of producing megathrust earthquakes. So, the region is now known to produce powerful earthquakes, but this wasn't always the case. For a long time, it was believed that the Cascadia subduction zone was not a seismic hazard. This was a reasonable belief to have because most subduction zones around the world had frequent, high-magnitude earthquakes. Some subduction zones even output magnitude 9 earthquakes on the Richter scale, but Cascadia had just remained silent. This was initially believed to be due to the Juan de Fuca Plate no longer subducting beneath the North American plate, but this was disproven in 1980 upon the eruption of Mount St. Helens. For this dramatic geological event to occur, subduction had to be occurring. So, then it was thought that the lack of earthquakes in the subduction zone was because there was not sufficient seismographs. But the USGS, University of Washington, and the Geological Survey of Canada have deployed a vast network of seismographs that recorded earthquakes in the Juan de Fuca Plate and the continental crust, but still, none in the actual subduction zone. Furthermore, when the US Navy opened access to its hydrophone arrays, which were technology capable of detecting submarines, whale calls, and earthquakes, the subduction zone remained quiet. So, members of the geological community concluded that the only possible explanation for the lack of seismic activity must be the way the Juan de Fuca Plate is subducting. They believed that the plate was smoothly slipping beneath the North American continent, avoiding all seismic activity. Of course, in the early 80s, researchers began to question these past beliefs. The reason for no seismic activity in the Cascadia subduction zone was because the Juan de Fuca Plate is completely locked. This conclusion subsequently led to the conclusion that the subduction zone is building strain at 1.6 inches per year, until it eventually will let go as a megathrust earthquake. Even with this conclusion, scientists still debated whether the Pacific Northwest faced an earthquake threat. This debate lasted until the Oregon Academy of Sciences meeting in 1987, where researchers agreed that the Cascadia subduction zone does indeed pose a massive threat. But so many more questions remained. When will the megathrust earthquake occur? What will the magnitude be? And why are there no earthquakes in Cascadia now? The lack of seismicity in the subduction zone was determined to not be sufficient evidence for the lack of subduction zone earthquakes. And so, the research continued. The imminent danger of a megathrust earthquake in the Cascadia subduction zone is upon us, so it's important to look at the history of earthquakes in the region. We have already discussed the 8.7 to 9.2 magnitude earthquake that occurred in the year 1700, but many more earthquakes have occurred in Cascadia's past. Using marine and land records to interpret Holocene paleo earthquakes, it was determined that earthquake recurrence intervals increase from south to north. The intervals increase from roughly 200 years in the south to every 500 years in the north, near Washington and Vancouver Island. Based on current data, there is a 20 to 30% probability that a megathrust earthquake will occur in the southernmost region of the Cascadia subduction zone in the next 50 years, and a 10 to 15% chance that the earthquake will rupture the entire subduction zone. This data is concerning and puts the possibility of a catastrophic earthquake into perspective, but recent efforts to monitor the risk of earthquakes have been deployed, and the data has been extremely important for both prediction and risk assessment. Through drilling and monitoring, researchers work to understand and mitigate tsunami and seismic risk in the Pacific Northwest. Subduction zones form where a thin, less buoyant oceanic crust descends beneath a thicker, more buoyant continental crust. The term buoyancy refers to the density of converging tectonic plates. The denser oceanic plate is capable of easily subducting beneath the less dense, more buoyant continental plate. As a result, a pair of parallel mountain ranges tends to form. The coastal mountain range, consisting of sedimentary strata and hard rock, is known as the accretionary wedge. It is formed due to material being scraped off as the oceanic plate subducts. Further inland, the volcanic range, known as the volcanic arc, is formed. The subducting plate releases hot water, which rises and melts the rock in its path, forming the volcanic arc. Between the oceanic trench and the volcanic arc is the region known as the Forearc Basin. At the Cascadia subduction zone, the Juan de Fuca Plate is the oceanic plate subducting beneath the North American continental plate. The Juan de Fuca, or JDF plate, subducts northeastwardly at a convergence rate of 3 to 4.5 centimeters per year. The JDF plate itself is relatively young, at less than 10 million years old. It is also quite small, only a few hundred kilometers wide from the center to the trench, making the plate very warm. The volcanic arc, or cascades, initiated volcanism roughly 40 million years ago. The most recent prominent event was the volcanic eruption of Mount St. Helens in 1980. The last megathrust earthquake occurred in the year 1700, and it's predicted that the megathrust earthquakes occur at the Cascadia subduction zone every 300 to 500 years. We are 323 years into this time window, making the geodynamic understanding of the subduction zone critically important. The Juan de Fuca Plate is a remnant of the Farallon Plate, which has been subducting beneath North America for the past 180 million years. The majority of the Farallon is believed to have subducted deep into the mantle beneath North America. Subducted slabs can be imaged as high-velocity features by seismic tomography. The process sends seismic waves through the Earth, and many high-velocity anomalies have been detected between 300 and 1200 kilometers beneath central and eastern United States. These anomalies are believed to be the remnants of the subducted Farallon slab. The accretionary wedge formed is known as the Coast Range. Prominent mountains include the Olympic Mountains, which are made of oceanic sediments and hard rock from the subducting Juan de Fuca Plate. As the Juan de Fuca Plate subducts, material is scraped off the top and the coastal range forms. Further inland, the volcanic arc is known as the Cascades. Prominent volcanoes include Mount Rainier and Mount St. Helens. The Forearc Basin in the Cascadia subduction zone is the Willamette Valley in Oregon and the Puget Sound in Washington. But the most important feature of the subduction zone is the locked zone. This is where the Juan de Fuca Plate is locked together with the North American Plate. This is the zone where earthquakes originate, making them crucial to understand. To understand how earthquakes work, one must first understand that rocks are elastic. Rocks in the brittle crust change shape under pressure, but return to their original form when the pressure is released. However, if too much pressure is applied, the rocks will break. Deeper in the earth, rocks behave differently and deform permanently, unable to return to their original form when pressure is released. Due to plate tectonics, plates grind past each other and come in contact, slowly building up pressure until they break, where the strain is released as an earthquake. The fracture zone or fault is where this occurs. Where a fault has a dip or inclination, the rock above is called the hanging wall and below is called the footwall. If the hanging wall moves up with respect to the footwall, it is called a reverse fault. This is the type of fault that exists at the Cascadia subduction zone. The process of an earthquake is quite complex, and there are people who dedicate decades to researching these natural events. For our purposes, all you need to understand is that tectonic plates grind past each other and occasionally get stuck. This builds up stress, which is eventually released in the form of waves, which shake the Earth's crust. This shaking is the earthquake. In the Cascadia subduction zone, this stress has been building for hundreds of years, and when the stress is released, the earthquake will be devastating. This is what occurred in the year 1700, and what will inevitably happen again because the plates are once again locked and ready to let go. The majority of the Pacific Northwest would be devastated by a magnitude 9 earthquake like the one that occurred in 1700. If the oncoming megathrust earthquake is magnitude 9 again, the shaking would last 2 to 3 minutes or even longer. Intense shaking for this extended duration would most certainly destroy buildings, bridges, and many other structures, taking and destroying many lives in the process. Furthermore, the earthquake would trigger landslides throughout the mountain ranges and continental slopes, potentially triggering tsunamis. It is predicted that the Pacific coastline would plummet 2 to 4 feet, inundating low-lying regions. Tsunamis up to 40 feet high would occur numerous times and destroy many coastal and inland structures. Aftershock earthquakes would occur at a diminishing rate for many years, bringing more destruction to the region. Besides the physical destruction, the economy of the region would plummet and would affect the entire United States and Canada. A magnitude 9 earthquake would be devastating for the region, but there are arguments that the region will undergo several smaller earthquakes rather than one big one. This argument is supported by the uplifting of southern Oregon and northwest Washington, but no lifting in central Oregon and the region around Gray Harbor, Washington. This observation led to the conclusion that only some regions are building elastic strain. Thus, the areas of no strain would prevent the rupture from continuing through the areas of intense strain. This would mean that several smaller earthquakes would occur rather than one big one that traveled the entire coast. However, others argue that the earthquake will be magnitude 9 due to the free-sliding nature of the subduction zone because of the high temperatures at greater depths. Currently, most members of the field believe that the earthquake that occurred in 1700 was magnitude 9, but this does not mean that the next one will be. The general conclusion is that the Cascadia subduction zone has not built up enough stored energy to yield a magnitude 9 earthquake in the next 50 years. The more likely scenario is a 7 magnitude earthquake in the northern region of the subduction zone and an 8 to 8.6 magnitude in the southern region. The damage would still be extreme, but would be much more confined than a rupture along the entire subduction zone. However, there is still much to learn, and this conclusion could be refuted at any time. The Cascadia subduction zone is equally scary as it is exciting, but its understanding is of utmost importance because it will affect all of us in the future, one way or another.